Hello and welcome back. In this lesson, we are going to look at pseudo-inverse. Pseudo-inverse. And the question is, why do we need the pseudo-inverse? So in associative memory that we have been looking at in past couple videos, every stored pattern is represented by a pair, as we saw, PQ, comma TQ. That is to say, every pair is a input output pair. Mm. And here the queues in the queue that we have, the queue simply represents the number of inputs. So if queue could be one input, two inputs, all the way up to uppercase key inputs. So this is the input pattern that we have, and then this TQ is the output or target pattern, and this is what we want the network to output when it receives any input PQ. So to make this happen, what we need is a single weight matrix W such that W PQ is equal to TQ for all Q. So this is good if all the patterns PQ were orthogonal. So if they are orthogonal, non-overlapping, so let me write that down here. If PQ is orthogonal, non-overlapping, linearly independent, and we had only few of them, then the Hibs rule that we have looked at, it works perfectly. And so the relation that we have seen before, that is W is equal to summation Q is equal to 1 to Q TQ PQ transpose, that works very well, and it gives us the each time we have input P that is orthogonal, we do get the exact target output. And here each association that contributes each association contributes cleanly to W without any interference or interfering with other associations. And so if you recall, we said that let me write that down, A is equal to W PK, and that is TK. So the output that we get, which is the target output for any new input PK, it's the exact match. So there is no error in the output, which is good. However, the problem starts when the inputs are not orthogonal, and in the real world, uh, the patterns are more likely to be not orthogonal. So they are input is likely not going to be orthogonal. And what that means is that the patterns can overlap. So patterns can overlap. uh, for example, images can share pixels and signals can share components. Vectors could point in similar directions. So the dot product pi transpose pj, this may not be equal to 0. And so when when the input patterns overlap, each Hebbian outer product that we calculate when updating the W, which is TQ PQ transpose, this that we uh, um, add to previous outer products to get the W, also adds error, and this unwanted error uh, sort of um, uh, is also shown in the output later on, uh, so that the output that we get when we use this particular W pk is not equal to tk as it did before. So here it was here there would be error, and therefore the output won't be exactly equal to what we expect, which is the TK. And so the associative memory, in a sense, corrupts previously stored patterns as soon as we add new ones to it. And the solution then is to get a target that is approximate. So what we are looking for here is WPQ is approximately equal to TQ. And this would work even if the patterns are similar, they share information, they overlap, they are not orthogonal. Um, and so how does this work? So there are a couple of things that happen. We need to do is unmixing. We need to unmix the overlapping patterns mathematically and then produce the best possible mapping from inputs to outputs in cases where the exact solution, as we saw in the orthogonal case, does not exist. So we do that by reducing the total error or all the patterns simultaneously, and then provide a unique stable minimum error solution in the end. The key idea here is that the WPQ is equal to TQ. So this is impossible to calculate when the patterns overlap, and so we use a numerical approach uh, to minimize the total error, where we use the relation. uh, we take the Frobenius norm of this T minus WP, uh, and then square of that, and what that gets us is W is equal to TP plus, and this TP, this last part right here, that's the that's the Moore-Penrose pseudo-inverse, uh, pseudo-inverse of the input matrix. And this gives an optimal associative memory mapping. That is to say, it gives us the closest possible value of the target with minimal error as possible. And here the P plus can be written, is given by P plus is equal to P transpose P inverse of that and dotted with P transpose. So that's sort of the main idea here. And we'll look at how this is derived as in this video. So in summary, what we need is a pseudo inverse, and that is because the Hebbian learning fails when the input patterns overlap, and this pseudo inverse mathematically sort of unmixes the patterns and gives you the best possible mapping from the inputs to the targets with minimum error. So let's now get into the actual derivation part of it. So what we want is matrix W. Let's write that here. Matrix W such that for every training pair, WPQ is equal to PQ, where Q is equal to 1 all the way up to uppercase Q. And all the inputs are going to be in the matrix P. So we collect all the inputs as columns of RQ, columns of the matrix P, which we can write as follows. So we say P is equal to P1, then P2, all the way up to PQ, and this has the shape RQ. So each input P1 would have sort of the number of rows R, and it will have just one column. And when we put such multiple inputs in a matrix, we have Q inputs with R rows. So that's what we have there. And then all the targets also as columns. So T is equal to T1, T2, all the way up to TQ, and this would be of the shape S by Q, and that is because our matrix W. So here's the W matrix. So the W matrix that we have would have the shape S by R. The P matrix would have shape of R by Q, and so when we dot these two, what we get in the output is the target matrix, which would have the shape S by Q. And so here, so the mapping that we are interested in is the following: WP. So WP is equal to T. Usually this cannot be solved exactly unless the input patterns are orthogonal, these P, and the span is the and span the correct space. So what we try to do is find the best approximate solution, minimizing the total error. And so here is what we do: we define the error matrix. So error matrix, and what we do is for each input pattern PQ, network produces WPQ. So the column of Q of WP, and the target is TQ. And so the error is EQ is equal to TQ minus WPQ. And when we stack all the errors, we can write this in the form of a matrix: uppercase E is equal to uppercase T minus WP, and which would have the size S by Q. And then we can define our cost function or total energy. In simple terms, what we try to define is a way we can find uh, that this difference between the T and the WP is as small as possible. And for that, we cannot use this matrix to find that. Well, we need just a single value, a scalar value, and to get that, what we do is we take the squared Frobenius norm of this relation. So what we say is f of W is equal to norm of E, which is the same here if we substitute the values for E, which is this one. And if we expand this, what we get, so we expand this, and that gets us W. F of W is equal to sigma I is equal to 1 to S, sigma Q is equal to 1 to Q, in parenthesis T IQ minus WP IQ squared. And here, if you are wondering how we got this, so this part is simply, so WPIQ is simply summation. This is R is equal to 1 to R WR, sorry, WIR PRQ. And notice that if you look at a couple of previous videos where we have expanded W and P, you'll realize that we are dotting the rows of W with columns of P, and that gets us this part right here. So the FW is equal to norm of squared norm of T minus P, T minus WP squared is equal to trace of T minus WP and T minus WP transpose. And if we differentiate this with respect to W, what we get is minus 2 T minus WP P transpose, and this is the standard matrix calculus. So if we have a partial with respect to W of A minus WB squared, we would get minus 2 A minus WB B transpose. So we set the derivative to 0. So what we have is minus 2 P minus WP P transpose is equal to 0, and thus we have T minus WP P transpose is equal to 0. So that's the normal equation for least squares. So we can rewrite this as WP P transpose is equal to TP T, and this equation must be solved for W, and here we need to remember that each pattern PQ each pattern PQ has the length R, and there are Q patterns there, and oftentimes R is greater than Q, and these patterns PQ are linearly independent, and what this means is PTP is a Q by Q matrix, and it is invertible, but P P transpose is R by R matrix, and it is not invertible because uh, rank and that's because rank less than Q less than R. And so we do not try to invert this PP transpose. We do not try to do this. And so what we do instead is bring in the Moore-Penrose pseudo-inverse. So the pseudo-inverse P plus, let's write that here. So the pseudo-inverse P plus is defined as a unique matrix that satisfies the following: P plus P is equal to P. Then it needs to satisfy P plus P plus is equal to P plus. It also needs to satisfy P plus transpose is equal to P plus, and it needs to satisfy P plus P transpose is equal to P plus P. And therefore, for a matrix P, let's create another page. So for a matrix P with full column rank, the pseudo inverse can be written as P plus is equal to P plus P inverse and then P transpose. So when we solve for W, where we need a least squares solution for WP is equal to T, we multiply both the sides by P plus. So we say WP P plus is equal to TP plus, and here we know that the one of the pseudo inverse properties is that P plus is equal to I, because the columns in P are independent. Therefore we can write W is equal to TP plus, and we can finally substitute this in the equation above. So what we get is W is equal to T P transpose P inverse P plus. That's the final relation that we have, uh, which uh, which cleanly comes from a normal equation with the pseudo inverse identity.